Okay, so we start our solutions unit by going through like what a solution is, kind of reviewing what that means, the parts of a solution, and then the different types of the solutions we're going to see. So here we go. Some vocabulary we should know. So the first word we need to understand or know is the word solute. And the solute is the substance that actually gets dissolved. So if you're thinking about like making iced tea or hot chocolate, it's the powder that you put into the water that is going to be your solute. It's the thing getting dissolved. It's usually the smaller part of the solution. Not always, but typically it is the smaller of the two parts of that mixture or solution. A solvent is the thing that does the dissolving. The solvent is the dissolver. So usually water is our solvent in the chem lab. When you're making tea or coffee or hot chocolate, water is again your solvent. It's usually the larger part. You usually have more solvent than solute. And a solution, a true solution, is a uniform mixture. So it means it's the same throughout. It's homogeneous or homogeneous. It's the same throughout. It's made up of at least one solute and a solvent. Okay, so to be a true solution, there can't be any difference throughout. So imagine like a can of pop, like a can of Coca-Cola or Pepsi or something. If you took a sip at the top, like the first sip, the middle, you get halfway through the can, the next sip, or the very last sip, they should all be the same. Doesn't matter where you are in that can, it should be the exact same solution, same composition all the way throughout. So we dissolve solute into the solvent. Now again, homogeneous solutions are things that are the same throughout. So it's always a single phase. So if we're talking about like coffee, tea, pop, whatever, it is the same everywhere. So some examples I just gave you were like coffee, tea, pop, whatever. But if we're talking about a heterogeneous solution, I wouldn't even call it a true solution. It's not the same throughout. We just call it a mixture. So like a salad you could think of it as a mixture or a solution. Yes, I know it's solids, but solutions don't have to be in liquid form. So you could take a salad and toss all the stuff into it. You could call that a mixture, but unless every part of that salad is evenly spaced throughout, it's not a true solution. So it's heterogeneous. It's different. Remember the prefixes, homo meaning same, and hetero meaning genius, or hetero meaning different, and genius meaning throughout. So a mixture that doesn't have uniform composition could be something like I said, a salad, a chocolate chip cookie, unless those chocolate chips are exactly spread out perfectly throughout. Also, it's not the same throughout because there's parts where there's chocolate and there's parts where there's not chocolate. Another example that's in the liquid form would be something like orange juice, like with pulp. The pulp doesn't stay in one place. It kind of settles out. So you don't have a true solution there. So I'm not going to write down the examples. I just kind of went through a few. So Kool-Aid's another one I put in there. Orange juice with pulp would be another example of a heterogeneous, and away we go. So believe it or not, solutions, again, don't have to be in liquid form. We can have gas solutions, liquid solutions, and solid solutions. So what we're going to do is we're going to look at, there's actually 9 different types of solutions that are possible. You could dissolve solid, liquid, and gas into a gas. You can dissolve solid, liquid, gas into a liquid. You can also dissolve solid, liquid, gas into a solid. So that's what we're going to look at. So the first one is we're going to look at gas solutions. So in each of these, our solvent, the larger part of the solution, is going to be a gas. And then into that gas, we're going to dissolve gas, liquid, and solid. So if we take oxygen gas and we dissolve it into nitrogen gas, in other words, we have a mixture of oxygen and nitrogen gas, a perfectly even mixture, that would be a true solution. That's a gas-gas solution. And a good example of that is the air you're breathing right now. Now, it's hard to take a picture of air, so I took a picture of a skyline, but the air in the atmosphere is a solution of oxygen gas dissolved in nitrogen gas. Nitrogen being the bigger part, oxygen being the smaller part. Air, we can use air as our solvent, and into air, if we have liquid water in the air, we actually will have like fog or clouds, things like that. And you can think of that as a liquid in a gas solution, so moist or humid air. Now, again, we can also, I'm kind of air quoting the word dissolve, but dissolve solids into gas. If you think about like carbon into air, solid carbon, that's basically smoke. So the smoke you see coming out of a smokestack or a train engine like that, that's carbon going into the air. So you have carbon, solid carbon, dissolved in air. Dust in your house is another example. There's dust flying through the air. You can't see it, but it's mixed in with the air, and eventually it does settle out, but the dust is kind of dissolved in the air and suspended in that air. Now, we're going to have liquid solutions. We're a lot more familiar with liquid solutions because it's kind of the mixtures we tend to do or tend to have. So here's an example. We dissolve into water. So water's our solvent. We dissolve carbon dioxide. So this would be carbonated water. So this is what makes pop fizzy. A lot of people think they don't realize that you can dissolve gases into liquids. The carbon dioxide here is actually being dissolved into the water or into the liquid, and then when you open the can or whatever, it can or change the pressure or the temperature, it can bubble out of that solution. So it's not super stable, but carbonated water would be example. So the fizziness in pop, it's actually carbon dioxide that's been dissolved into the pop. It's evenly dispersed throughout, and eventually it will leave the solution. Gases don't like to be dissolved. Another example is in water. There's always dissolved oxygen, and this is how fish breathe. A lot of people think that the fish, when they breathe water, they're breathing water. They're actually not breathing water. They're not taking the oxygen out of water, because if they did that, you'd be left with hydrogen gas. So every time they breathe, hydrogen gas would be bubbling out of a lake, and you could have an explosion. That's actually not what's happening. In the water, so if you have a bunch of water molecules, you have oxygen gas that's surrounded by them. So there's an oxygen gas molecule that's dissolved in that water. And when the fish pass that water over the gills are able to pull the oxygen out of the water out of the water solution, much like our lungs pull the oxygen out of the nitrogen solution. So same idea, it's just the solvent is water rather than nitrogen. Here's another one, water and ethylene glycol. Ethylene glycol, we better know it as antifreeze. So we mix antifreeze and water to use as a coolant or an antifreeze in our car engines. Why is there a cat beside that? Well, it's from a public service thing, because antifreeze apparently tastes sweet. Shouldn't taste it, by the way. But it's also toxic, so if you have a spill, lots of animals will actually be attracted to it, and they'll eat it because it tastes sweet, and it ends up poisoning them. So I think that's where I got that image from. Water is a liquid, and solid is sodium chloride. Here's the biggest solution on Earth that we have with solid salt and water is ocean water. So that would be an example of another mixture solution. So that's a solid liquid solution. Now we can also dissolve things into solids. Now it's, these were maybe not as familiar to us, but it can happen. So we can dissolve gases into solids. So this is actually one way they're talking about capturing carbon dioxide out of the atmosphere, is to dissolve it into bedrock and mineral rocks in the earth and kind of remove carbon dioxide that way. We can also use carbon, charcoal, like solid carbon, as a solvent to dissolve poisonous gases and trap them in the solid. And that's where we use charcoal filters. So it's you can use that for gas masks and things like that. Another one is silver. If we dissolve mercury, which is typically a liquid, into silver, so to dissolve it, we actually have to melt the silver down and then add the mercury. But when we mix those two, you get what we use for tooth fillings. So a small amount of mercury with a silver. Copper, we can dissolve stuff into copper. If we take zinc, solid zinc, and dissolve it into solid copper. Now, how would we do that? They're two solids. We would melt them down and mix them together. So basically, in this case, you're making brass. But any alloy, so brass, bronze, steel, anytime you're mixing two metals together, that would be a solid solution because you have two solids mixed together. Now, when we're talking about dissolving, oftentimes we're going to be dissolving things in water. So our structure of water becomes important. We talked about the alchemists way back, and they were looking for the universal solvent. Well, it turns out water is probably our best thing or closest thing to a universal solvent, and it's got to do with the structure of water. Before we talk about that, we have to talk about something called electronegativity. And electronegativity is the ability of an element to attract electrons in a bond. It's how strong of a pull elements have, or atoms have, on electrons. So when you have two elements that have very different pulls on electrons, you can get an ionic bond. One takes electrons from the other. But sometimes you get two elements that are fairly close in strength, and they end up sharing their electrons, and we've been talking about covalent molecules. Up until this point, all bonds have been either covalent or ionic. Now there's kind of an in-between. It's actually not this or that. It's actually varying degrees of ionic and covalent. And in the middle, we call them polar. They're kind of ionic and kind of covalent. They're kind of in the middle. So what ends up happening is you get an unequal sharing of electrons. So here's what a water molecule is going to look like if you show where the electrons are. So we have our oxygen and our hydrogen. If you imagine this black line I just drew as the bond between those two, you see where the electrons are, they've actually been pulled closer to the oxygen. And the reason for that is oxygen has a stronger desire pull on electrons. It's got more protons in its nucleus. It's going to pull the electrons closer to itself. It wants to gain electrons more than hydrogen wants to gain electrons. So what ends up happening is now because the electrons are spending most of their time close to the oxygen gets a slight negative charge. And that's what that little, this is actually the Greek lowercase d, delta. It's kind of a D like this, and that means partial negative. So that's our symbol for partial. So you get a slight negative charge on the oxygen side, and because the hydrogens have kind of lost their electrons, they've kind of become positive. So we get this slight positive and negative side to the water molecule. And that's what I'm saying here. The oxygen's more electronegative, so the electrons in the bond orient themselves more completely or more often around the oxygen atom. And I just put a note that little symbol, the Greek letter delta, means partial. You guys know the capital letter delta is a triangle, means change in. This means partial or slight. So why is this important? Well, water now it's polar, so it has charges, and it can attract lots of things. If you've ever seen the bending water trick with a stream of water coming out of a tap and you charge something up, rub like a balloon on your head, bring it close to the water, it actually will bend the water, showing that water actually has some charge. It actually attracts. It will attract to either the positive side or the negative side of the water molecules. But that attraction, that slight charge of water allows it to dissolve many, many things. Okay, a few more things in terms of vocabulary we need to talk about. So the word soluble means the ability to dissolve. So something is soluble, it is able to dissolve. That's kind of what it means. So salt and sugar are soluble. If something is insoluble, it's not able to dissolve. It's unable to dissolve. So like, for example, diamonds are insoluble in water. Lots of things we would call them not soluble or insoluble, like a rock. We would say a rock doesn't dissolve in water. But if you have enough water flowing over a rock over time, it does dissolve it a little bit. So water will dissolve things to varying degrees. Some things are very soluble, some things are not very soluble. Now, when we're talking about liquids, we tend to use different terms for that. So if two liquids are able to mix, we call them miscible. And the way, when you say it, it actually almost sounds like mixable. Miscible. And so water and vinegar mix, water and alcohol mix, but oil and water don't mix. And we're going to talk more about why that happens in the next parts of this unit. So water and oil are immiscible, whereas water and vinegar are miscible. Now, here's where we get into something of huge importance, especially in the grade 12, is what happens when things are actually dissolving. So we have to imagine what's going on at the molecular level in the water when we dissolve things like salt or sugar. Now, when we dissolve salt at the molecular level, salt is composed of sodiums and chlorines. And if you kind of notice the way it's diagrammed in these images here, the positives and negatives alternate spots. And that's what gives salt its very stable and very strong arrangement and structure. Because everything's kind of packed together nice and neat, goes positive, negative, everything's kind of all together just the way it should be. And then if you look at water, water also has, well, this is why water has such good surface tension, it stays together fairly well, because water actually also has some positives and negatives, and it kind of aligns itself so the positives and negatives are attracting again. And that's what keeps water kind of together. But why would salt, if we think about this, why would salt dissolve into water? Well, the positives are attracted to these negatives on the salt molecules, and The negatives are attracted to the positives of the salt molecules. So there's an attraction between the water molecules and the particles, the ions that make up your salt. So that's what I'm saying here. So why do we think sodium chloride would dissolve in water? Because the polar water molecules have an attraction to those ions, the Na pluses and the Cl minuses. Now, if you imagine you drop a chunk of salt into the water, where does that dissolving process start? It starts at the surface. So if you imagine you have a chunk of salt, the blue and green little circles on here are representing the positives and negatives of the salt ions. The water is going to start attacking the outside of that chunk of salt, and then it's going to work its way in. Everything dissolves from the outside in. The more, we'll talk about how to make things dissolve more quickly, but the more surface you have, the more things, and not maybe the more, but the more quickly things will dissolve, and more easily maybe they will dissolve. So now, how does this happen? So if we're dissolving water or salt into water, the water actually rips apart the sodiums and the chlorides. This is probably the most important concept that we have in this part of the course. The NaCl's, if you notice, the chlorine, so there's my chloride I should say, chloride ion, it's being surrounded by water molecules. And if you look at the way the water molecules are lined up, the positives are all pointing towards the chloride because the positives are attracting to the negatives. And then if we look at here, here's our Na plus. If you look, the way the water's arranged itself is the negatives are all attracted to the positive. The water kind of flips over for the sodium ions. And what's really happening is the salt crystal is being ripped apart into its ions. And that's really special because it actually creates something called an electrolyte, and we'll get to that in a second. So in order for this to happen, there's three things. In order for anything to dissolve, there's three things that have to happen. The solute, this stuff, whatever you're dissolving, has to be broken apart. The solvent, the water, has to be broken apart. And then there has to be an attraction between the solute and the solvent. And so we have breaking bonds or attractions and making bonds or attractions. And we'll talk about energy changes in that in a little bit. Now, when we're dissolving ionic compounds, some compounds will dissolve and they dissociate. English teachers hate it when we say dissociate because it should be disassociate, but dissociate means to break apart. If two things are associated together, they go together. If two things are disassociated, they've broken up. So when salt dissolves, this is what it looks like. It makes Na plus and Cl minus. So what is dissociation? It's the breaking up of ionic compounds when they dissolve. And the reaction is called a dissociation reaction. So I'm going to show you right now a couple little animations of how this works. So imagine we have water, and we're going to add a chunk of salt. Looking at it at the molecular level, you see the Na pluses and Cl minuses, but what you also see is the water is ripping the ions apart. Super important to understand this part. You'll also notice that the red side, the oxygen side of the water, should be grabbing onto the sodiums, and the yellow side should be grabbing onto, sorry, that was a wrong one. The yellow side should be grabbing onto the chlorines or chlorides. There is one that is wrong in this animation, but the hydrogens go towards the negatives and the oxygens go towards the positives. And what you end up with is a salt solution that has ions floating around in it. And because of that, this solution is called an electrolyte. Why? Because it can conduct electricity. You have charges that can move around. I have another animation I'll show. This one should work.
When an ionic substance,
Oh, I can't play this because it's a YouTube video. My apologies. The key here is, I'll play this actually one more time, just to make sure. The key that you need to understand here is that the ions are actually being ripped apart. And those ions can carry charges, and the movement of charges is electricity. So we can actually have electricity flow through this. So when you talk about Gatorade having electrolytes, it's because it's got salts in it. Maybe not table salt, but it might have potassium chloride, which is important to replenish the electrolytes in your body, other types of salts. Basically, any ionic compound can be called a salt. and that bottom one is the one that's wrong. But anyways, hopefully you get the idea. So if we want to write a dissociation reaction, this is what it looks like. So imagine we have aluminum sulfate. Again, this would be a salt because it's an ionic compound. So I have Al, need my pen, Al SO4. So it's Al2SO4 3. If we were dissolving this, it's going to break apart into aluminum ions and sulfate ions. I'm going to call this a solid to start. Now the problem here is it's not balanced. Notice though you have two aluminums on the reactant side. Well, two aluminums are from the AlSO4, it's going to dissociate into two aluminum ions. But we don't put the two here because that implies that those aluminums are stuck to each other. We're breaking it up into its ions that make it up. So the 2 goes here to balance it. And the same idea with the sulfates. The sulfates, there should be 3 sulfates being made, so this way we put a 3 there to make 3 sulfates. So we balance using coefficients here. We're making 2 aluminum ions and 3 sulfate ions. We're just taking that apart. Now when we're dissolving a covalent particle, this is a little bit different because there's no charges involved. Covalent molecules are whole molecules with very, very little charge, if any charge at all. And they don't dissociate. So when sugar dissolves, it actually doesn't break apart into ions or even atoms or anything. The molecules stay together, but the molecules get pulled out of the crystal as a whole molecule. Whereas NaCl didn't get pulled out as NaCl, it got broken into NAs and Cls. These molecules stay together. And you'll notice that it doesn't really matter which side of the water molecule is attaching because there's just a kind of a slight attraction between charged and neutral things. So when we dissolve covalent compounds, there's actually no dissociation. So if I ever ask you to write a dissociation for covalent, you can't because there is no dissociation. The solid just becomes a liquid, or I should say aqueous, and we'll talk about that in just a second. So I'm going to show you what this looks like in terms of dissolving some sugar. Same idea, same system, same everything, same white chunk of stuff going in, but instead of salt this time, it's sugar. Zooming into the molecular level. Now you see that the sugar molecules are actually being completely ripped apart by the water molecules. Now, they're being ripped apart as entire molecules, not being broken down into their substituent parts, if you will. Okay, so this time there's no charges floating around, so there's no ability to conduct electricity, so covalent molecules, when they dissolve, are not electrolytes. Clicking ahead, we call that solvation because you're getting surrounded by solvent. And if we wanted to write the reaction for that, so if I have octane, that's actually not octane, this is propane. I'll fix that. So C3H8. If we have solid, liquid, gas, in this case, we know propane is a gas, so I'm going to put it as a gas. If we dissolve it into water, you get C3H8, and it's aqueous. Now, what does aqueous mean? It means in solution, in water solution. I'm not sure if I did that on the previous page. I should have if I didn't. Yes, I forgot to write my states. So the state of this would be aqueous, and this would be aqueous. So these ions are in water, in solution. Aqueous, think of like aqua, water. So anytime a substance is dissolved by water, we can call it hydration. You're adding water. Now, how is dissolving covalent compounds different than dissolving ionic compounds? Well, covalent compounds separate into their molecules, whereas ionic compounds separate into their ions. And that's what this looks like. So covalent is a lot different than ionic. One's an electrolyte, one is not. Here's a way we can put it all together. So if I put salt into water, we can test its conductivity. It's conductive, right? If we reset everything and we switch it to sugar, I put sugar into water, make this bigger, and then I test its conductivity, and the light bulb doesn't light up at all. Now, if we want to see this a little bit more closely, see what's actually happening, well, we know salt is actually sodium chloride. So when I put sodium chloride into the water, I'm adding Na pluses and Cl minuses. But if you look, the Na pluses and the Cl minuses have separated into separate Na pluses and Cl minuses. And that's why this is conductive, because you have positive and negative charges. Now, if I reset this and I go to sugar, and I dump in a couple big sugar molecules, notice they're huge molecules, the molecules as a whole dissolve, but there's no ions. They don't break, the molecules don't break apart into smaller things. Now, if I go even closer, so if you imagine water at the molecular level, it's got all these little H2Os all moving around like crazy inside. If I dissolve salt into it, you're going to see that the water molecules basically, look at the red side is grabbing onto the sodium, and if you saw the chlorine, the white side of the water would be grabbing onto the chlorines, but they've just kind of got pulled apart into the solution. But if I reset and I go to sugar, the entire molecule gets surrounded by waters. So it's a little bit different. All right. Which of the two solutions conducts electricity? The ionic one, because it has charges that can move. Now I'm going to stop the video here because I want to talk about the heat of solution in a little bit more in depth. So this will be the first part of the introduction video.